Welcome to the section on corrective measures. To correct some of the problems we may face while training the GANs, the W-GANs, or better still the Wasserstein GANs, were developed. In this paper by Martin Arjavsky, Sumit Shintala, and Leon Botou, they actually present in depth the Wasserstein GAN. Now, for the contributions in this paper are they provide a comprehensive theoretical analysis of how the earth mover distance behaves in comparison to popular probability distances and divergences used in the context of learning distributions. Also, they define a form of GAN called the W-GAN that minimizes a reasonable and efficient approximation of the EM distance, and they theoretically show that the corresponding optimization problem is sound. They empirically show that W-GANs cure the main training problems of GANs. In particular, training W-GANs doesn't require maintaining a careful balance in training of the discriminator and the generator, and does not require a careful design of the network architecture either. The mode dropping phenomenon that is typical in GANs is also drastically reduced. One of the most compelling practical benefits of W-GANs is the ability to continuously estimate the EM distance, that's the earth mover distance, by training the discriminator to optimality. Plotting these learning curves is not only useful for debugging and hyperparameter searches, but also correlate remarkably well with the observed sample quality. Now let's look at the different distances which are involved in the GAN literature. We have the total variation distance, the Kullback-Leibler divergence, the Jensen-Shannon divergence, and the earth mover distance. Now, you may have seen this Kubler, or we have actually seen this KL divergence previously, and looking at this formula, you recall what we saw under the GANs. But this wasn't actually used in the GANs. What was used in the GANs was the Jensen-Shannon divergence, which was used to represent the optimization problem in the discriminator for the GAN. Now with the W-GANs, they introduced this earth mover distance, or Wasserstein 1, where the EM distance between two distributions PR and PG is given as the infimum of this expectance, where X and Y are taken from this distribution gamma, and gamma belongs to this pi PRPG, which actually denotes the set of all joint distributions whose marginals are respectively PR and PG. Also, intuitively, gamma of xy indicates how much mass must be transported from x to y in order to transform the distributions PR into the distribution PG. The EM distance then is the cost of the optimal transport plan. Now, in the following example, we shall see how apparently simple sequences of probability distributions converge under the EM distance, but do not converge under the other distances and divergences defined above. Now, we define Z to be a random variable from this uniform distribution on the unit interval. Now, let P0 be the distribution of 0 and Z, both taken from R squared, where 0 is on the x-axis and the random variable Z on the y-axis, uniform on the straight vertical line passing through the origin. Now let G theta of Z be equals theta Z. So instead of 0 Z, now we have theta Z, where theta is a single real parameter, and we could plot this out like this. So right here we have P0, and then here we have P theta. We see actually this is like the x-axis, and then this is the y-axis. So right here we have 0, and then here we have the value theta. So recall we had defined in the paper was defined 0 Z element of R square. So this is 0, and then this is the uniform distribution, which goes from 0 to 1. That's on this y-axis, it goes from 0 to 1. On the x-axis is found at the point 0. Whereas here it goes from 0 to 1, and then here it's at the point x equals theta. So this is our p theta, which can take any value. So theta could be anywhere around this. Now in the paper, they actually calculated the EM distance, which gave the absolute value of theta, the GS divergence, which gave log 2 when theta is different from 0, and 0 when theta is equal to 0, the KL distance, which gave positive infinity for theta different from 0, and 0 for theta equals 0. And then also the TV distance, which gave 1 for theta different from 0, and 0 for theta equals 0. So from this, we see clearly that when theta t is turning towards 0, the sequence p theta converges to p0 under the EM distance, as we could see right here, but doesn't converge at all under either the GS scale, reverse scale. This is actually the reverse scale. If this is the scale, for example, then this is its reverse scale. So we have the reverse scale, the TV divergences, which do not converge. And the reason why we have this is actually because, as we could see, it's only the EM distance that has a continuous value for all the values of theta. We see that for the GS, there is some discontinuity at theta equals 0, for this at theta equals 0, and for this at theta equals 0. So only this actually gives the same value for all values of theta. Now let's show how they got those values in the paper. We had defined the KL divergence to be this, the GS divergence to be this. We have seen this already. Now let's calculate the KL divergence, where we have P0 and P theta. So we've had this, we have this P theta, P0 distribution, and then the P theta distribution. Now we're having x equals 0, and then y is taken from the uniform distribution, which goes from 0 to 1. As we have seen, we're actually going from 0 to 1 here. Then simply applying this formula where we have P, now P equals P0 or P0 rather. So we have this P is equals this P0, and then this Q is the P theta. So when we find P0 when x equals 0, we actually have a value of 1, because this P0 when x equals 0, we obtain the value 1. Now when we have Q, that's the P theta, when x equals 0, actually gives us a value of 0, since P theta is at this point where we have x equals theta. So actually this is 0 right here, since this is P theta when x equals 0. So that gives us 0, and calculating this gives us 1 log of 1 divided by 0, which is infinity. That's exactly what was getting in the paper. Now we also have that when this theta right here is equal to 0, these two distributions overlap. So in that case, we'll obtain a value of 0 right here, since we shall have 1 log 1, since this will become 0. Now we move to the next. The KL divergence for P theta, that's a reverse KL divergence, P theta, P0. We have here x equals theta instead of x equals 0. We're now having P theta when x equals theta. That's P theta when x equals theta is 1. P theta when x equals theta is 1. P0 when x equals theta is actually 0. So this distribution when x equals theta is 0. So that's why we have positive infinity. And then we have also the GS divergence, which we could calculate. We have here from the formula that was given already. So we just basically apply this. We have P now, which is P0, and Q, which is also P theta, as we had defined earlier. So practically here, we're just applying the formula. And applying the formula here, we still have this 1. Since we had already found that when P0 is at x equals 0, we have the value 1. And then for Q, we have the value 0, because P theta when x equals 0 is actually equals 0. So we have 1 divided by 1 plus 0 divided by 2. This is a similar case here, and so we have 0 plus 1 divided by 2. This gives us log 2 plus log 2, and then divided by 2. That gives us log 2. So this is how it was got in the paper. Then right here we redefine we rewrite the EM distance given in the paper. Note that we've moved from xy to x1, x2, so that you see that actually this is computed between two x values, so between two values in this axis, and that's how we obtain the absolute value of theta, since we have these two distributions, the distance between this is actually theta. If this p theta is now found somewhere around this, we're gonna have a distance of say 0 minus theta, but we're getting the absolute value. So that's the role of this absolute value right here. We just get those distances very easily, and we note that actually whether we at the 0 point or for any other point on this x-axis, we'll always get the same answer, which is a function of theta. We now see on this plots a function of theta where this row is the EM distance, the left plot, this is the EM distance, and the GS divergence, the right plot. The EM distance is continuous and provides a usable gradient everywhere, whereas the GS plot is not continuous and does not provide a usable gradient. The authors actually also went further to say that since the Wasserstein or EM distance is much weaker than the GS distance, actually the GS divergence, we can now ask whether the EM distance is a continuous loss function on theta under mild assumptions. Now this and more is true, as it's now stated and proven. So here they actually define this PR, this fixed distribution over X, where Z is a random variable over another space big Z, and they define this function G that will be denoted G theta of Z, with Z the first coordinate and theta the second. Let P theta denote the distribution G theta of big Z. Then if G is continuous in theta, so is the EM distance between PR and P theta. And if G is locally Lipschitz and satisfy regularity assumption, then the EM distance between PR and P theta is continuous everywhere and differentiable almost everywhere. Statements 1 and 2 are false for the GS divergence and all the KLs. Now all this shows that the EM is a much more sensible cost function for a problem than at least the GS divergence. The following theorem describes the relative strengths of the topologies induced by these distances and divergences, with the KL the strongest, followed by the GS and TV, and the EM the weakest. Now according to theorem 2, the following statements are equivalent. We have the TV, which converges with sigma, the total variation distance, that's actually the TV distance, which converges, and then the GS divergence, which also converges, and these two statements are said to be equivalent. That is, if this converges, it means this converges, and if this converges, then this converges. Then also these two statements are equivalent, where we have this EM distance, which when it converges, then Pn would converge to P, that's the distribution Pn converges to distribution P, and if the distribution Pn converges to the distribution P, then W, or better still the EM distance, converges. Now we also have for the KLs, where we have the KL of divergence of Pn with P, which converges, or the reverse, which converges, implies that we have the statement 1, which is true, and the statement in 1 implies the statement in 2. So this implies this. Now this highlights the fact that the KL, JS, and TV distances and divergences are not sensible cost functions when learning distributions supported by low dimensional manifolds. However, the EM distance is sensible in that setup. This obviously leads us to the next section, where we introduce a practical approximation of optimizing the EM distance. So now is where we define the Wasserstein GAN. Again, theorem 2 points to the fact that the EM distance between PR and P tether might have nicer properties when optimized than the GS divergence, and however the info moment 1 is highly intractable. On the other hand, the KR duality tells us that this distance is equals the supremum of the expectance of f of x minus the expectance of this f of x. So where we have this x drawn from this probability distribution PR and x drawn from the probability distribution P tether right here. So this two are drawn from two different distributions, while noting that this is for f being a K-Lipschitz function. A K-Lipschitz function is a function which verifies this condition right here. So from here we note that if we replace this right here, because this one Lipschitz function as we define it right here, so if we replace this now with this, we end up with K of the EM distance between PR and PG, and therefore if we have a parameterized family functions that are all K-Lipschitz for some value of K, we could consider solving the problem maximum of the expectance minus this other expectance, where this x is drawn from the real data and then the z drawn from the fake data. Then this fw of x could represent the critic or the discriminator, and then this g theta of z represent the generated data, and then this generated data is passed through the discriminator. But what's important to note here is for us to get to this point, or we have actually assumed that we have these functions which are all K-Lipschitz. So from here we have the theorem 3 that states that if we have PR, which is any distribution, and P tether with the distribution of G tether of Z, where big Z a random variable with density P, and G tether a function satisfying assumption 1, which is that if J is continuous in tether, so is the EM distance between PR and P tether. Then there is a solution f to the problem maximum of this expectance, or the expectance of f of x minus the expectance of this f of x, where x and this x is drawn from PR and this x drawn from P tether, where we have f, which is K-Lipschitz, and we also have that the gradients of the EM distance between PR and P tether equals the negative of the expectance of this gradient with respect to tether of f of G tether of Z, where Z is drawn from PZ. Now comes the question of finding the function f that solves the maximization problem in equation 2. To roughly approximate this, something that we can do is train a neural network parameterized with weight W lying in a compact space big W, and then back prop through the expectance of the gradients of f of G theta of Z, as we would do with a typical GAN. Note that the fact that W is compact implies that all the functions fw will be K-Lipschitz for some K that only depends on big W and not the individual weights. Therefore, approximating equation 2 up to an irrelevant scaling factor and the capacity of the critic, which is the discriminator fw. In order to have parameters w lie in a compact space, something simple we can do is clamp the weights to a fixed box, say big W between negative 0.01 and 0.01 after each gradient update. So this kind of gradient clipping. The Wasserstein GAN procedure is described in algorithm 1. Weight clipping, that is limiting the weight to lie in a certain range, is a terrible way to enforce Lipschitz constraint. If the clipping parameters is large, then it can take a long time for any weights to reach their limits, thereby making it harder to train the critic till optimality. If the clipping is small, this can easily lead to vanishing gradients when the number of layers is actually big. So if the number of layers is big, and then we have a clipping width too small. This can lead to vanishing gradients. Or batch normalization is not used, such as in RNNs. Now we experimented with simple variants with little difference, and we stuck with weight clipping due to its simplicity and already good performance. However, we do leave the topic of enforcing Lipschitz constraints in a neural network setting for further investigation, and we actively encourage interested researchers to improve on this method. So right here we have the algorithm 1, where WGAN is a proposed algorithm, and then we have alpha as this. C, that's a clipping parameter to be 0.01. We have the batch size to be 64, and then the number of critics equals 5. Number of critics here actually stands for the fact that we're gonna train we're gonna update the discriminator parameters 5 times before updating the generator. So as you could see right here, for t equals 0 right up to n critic. So if you have n critic equals 5, from t equals 0 to 5, what we'll do is we're gonna collect the sample from the real data. We're gonna collect the noise data. Then here we update using RMS prop, where we define this GW right here to be, or the weights, or the derivative of the weights to be the difference between the real output of the discriminator and the fake output from the discriminator. And then after this, we clip the weights, as you can see right here. Then we now move to the generator. For the generator, we also use RMS prop, and just like for the discriminator, we also have the mean of the value. So right here we divide by 1 on m. Also here was done, and basically that's it for the algorithm. As we could see from this figure, with the density of a real data and the density of fake data, we have the GAN's discriminator with gradients, which is in red, as you can see right here, which turns 0 from a certain point, while the WGAN discriminator actually maintains linear gradients all through. So as you could see, the discriminator of a minimax GAN, that's the normal GAN, saturates and results in vanishing gradients, while that of the WGAN critic provides very clean gradients in all parts of the space. And we have the following results, where we have this MLP, that is multi-layer perceptron generator with 4 hidden layers and 512 units at each layer. And right here we have the typical GAN, typical DC GAN generator, and then the discriminator is both typical DC GAN. So we kind of like see the kind of results we get from this. We see how as we keep on training, as the loss is dropping, the results or the fake images being produced get better and better, and this shows that the training process becomes more stable. And this too can be noticed right here. We see this, as the loss keeps dropping, we get better and better images which are produced. Now this was run with the MLP, that's multi-layer perceptron generator and discriminator. We see here that the loss remains constant, and the quality or the kind of images being produced also remain constant. So kind of like notice that there's a correlation between the drop in loss and the quality of the images, or between the change in loss and the quality of the image. Now these plots show clearly that these curves correlate well with the visual quality of the generated samples. So that's what we just discussed above. Now, to the knowledge of the authors of this paper, this is the first time in GAN literature that such a property is shown, where the loss of the GAN shows properties of convergence. Now, this property is extremely useful when doing research in adversarial networks, as one does not need to stare at the generated samples to figure out failure modes and to gain information on which models are doing better over others. Now this is true as comparing with the GS estimate. The GS here is the GS divergence, which actually corresponds to the DC GAN. So comparing with this GS divergence estimates for an MLP generator, that's right here, and a DC GAN generator, which is here, shown with a standard GAN procedure, where both had a DC GAN discriminator, we have that both curves have increasing error, as you could see right here. And samples get better for the DC GAN, but the GS estimate increases or stays constant, pointing towards no significant correlation between the sample quality and the loss. And in this one right here, the MLP with both generator and discriminator, that's with as you can see here, we have the generator and the discriminator, which are actually MLPs. The curve goes up and down regardless of sample quality. So you can't just come at any time and like notice the pattern and say, okay, this is dropping, then it means the quality is increasing, or maybe this is increasing and the quality is increasing. So there's no correlations, as you can see. When it's dropping or when it's increasing, it doesn't actually correlate with the image quality, whereas right here there's a great correlation between the loss values we're getting and the image quality. After looking at the Wasserstein GAN, let's look at this paper, which comes with an improved training technique. This paper is by Ishan Gulrajani, Farouk Ahmed, Martin Arjavsky, Vincent Dumoulin, and Aaron Couville. GANs are powerful generative models, but suffer from training instability. The recent proposed WGAN, which is what we've just seen, makes progress toward stable training of GANs, but sometimes can still generate only poor samples or fail to converge. The authors find that these problems are often due to the use of weight clipping in the WGAN to enforce a Lipschitz constant on the critic, which can lead to undesired behavior. The authors propose an alternative to clipping weights, that is, penalize the norm of the gradient of the critic, that is the discriminator, with respect to its input. The proposed method performs better than the standard WGAN and enables stable training of a wide variety of GAN architectures with almost no hyperparameter tuning, including the 101 layer ResNets and language models with continuous generators. They also achieve high quality generations on the CIFAR 10 and the Elson Bedrooms dataset. In order to enforce the Lipschitz constraint, the authors came up with this gradient penalty right here. So apart from having the loss, that's the WGAN loss, which we've seen already, they added this loss to this gradient penalty to enforce the Lipschitz constraint. And then there is this gradient parameter or factor which we multiply with the penalty. This gradient penalty, as you could see right here, is made of the partial derivative of the output of the discriminator network when it takes as input this mixture, which we call, say, X bar, of the real data and the fake data. And this L to num minus 1 all square is what forms the gradient penalty. Then lambda is the gradient penalty weight. Also note that for every batch, this epsilon right here, or this factor, is drawn from a random distribution which lies between 0 and 1. Let's now go ahead and implement the WGAN. As usual, we load our data set. We're going to be using the select data set. Then for the modeling, we have the generator model. We have the discriminator model, from which we've taken off the batch normalization layers. So here we have no batch normalization layers. Then we go to the training optimization. You will have this discriminator loss, which is an application of what we had seen already. And so to get the discriminator loss, we would have to take the discriminator outputs from when the inputs are real data, like here, if we draw this from real data, we get these outputs, we sum them up, divide by the batch size, and subtract the discriminator outputs, or the sum of the discriminator outputs when the input is the fake data. Then we optimize the parameters, and then we also clip them. Nonetheless, we are going to use the gradient penalty method, so we are not going to use this. We are not going to apply this clipping right here. Then for the generator loss, we had seen that simply here we needed to sum the generator outputs when the input is fake data. And so applying that, we have for the discriminator loss, the reduce mean function of the outputs from the discriminator when it takes in real data, and then the reduce mean of the discriminator output when it takes in fake data. Then we simply subtract these two, giving us real loss minus fake loss as given in the paper. Then for the generator loss, we simply have the fake data which passes into the generator, and then we simply sum up all this and then get the mean value. Also be careful with this negative sign, as in the paper right here we have the real minus a fix, but note that here we instead have a plus instead of a negative as defined in gradient descent. So that's why you'll see in our implementation, since we are going to have, or since this is a negative, that's the gradient descent, this is going to be negative, we are going to interchange these two positions, since we will have minus of this value minus this value. Hence now we're going to have the fix minus the reals. And that's why right here we have fake loss minus real loss. So let's run this. Our learning rate is defined. Define the optimizer, number of epochs, number of critic steps, and then we'll have all this defined just like with a GAN. Also, just as it was defined in the initial GAN paper, after doing the optimization, we now clip the weights. So basically for all layers in the discriminator model, we get these layers and then we clip the values such that they don't go below a certain clip value or above this. So if our clip value says 0.01, our weights wouldn't go below negative 0.01 and wouldn't go above 0.01. And once this is done, we simply set the weights to this new clipped weights. Nonetheless, we are not going to be using this, so we take this off. Now let's define the gradient penalty function. So there we go, we have a gradient penalty function which takes in the batch size, takes in the real images, and also the fake images or the generated images. And the way it works is just like as we saw in the paper. We define the epsilon, which is drawn from a random normal distribution, and then the reason why we ensure that this epsilon's shape is the batch size by 1 by 1 by 1 is simply because we want that for each real image fake image pair there should be a value for epsilon. So this means that if our real image fake images come in as a batch, then each of those batches would have a different epsilon. And so as we could see here, we're generating this X bar, which is made of several batches and is given as epsilon times the real images plus 1 minus epsilon times the fake images. Once we generate the X bar, what we'll have to do now is to compute the derivative of the output when X bar is passed in the discriminator model with respect to X bar. Recall that this is what we consider to be X bar. Once we get this gradients, we compute their L2 norm, and then we use that else norm to obtain the final gradient penalty as defined in the paper. After getting the gradient penalty, we just get in here and then add that gradient penalty to the loss. So we'll have the loss plus the gradient penalty. Then we'll define the gradient penalty to be what we have here, this function. Simply we have gradient penalty, which takes in the batch size, the real images, and the generated images. Let's take this off, take off the clip value. We run the training, and that's the training which is started. After training for several epochs, you have the results we get. We see that initially we have this blank output, which is normal, and as we go, the outputs or the generated outputs start looking more like the images we have in the data set. You could see here. And as we go further, we even have better images. See that? And that's it for the section on the GAN.